right, so here I've got 3 simple circuits laid out that we can talk through and kind of compare and contrast. So here's just a single battery, and we hook it up to a single light bulb, and once I connect these two, the current will flow and the light bulb will light up. Now this one is going to be called a series circuit because the electricity is going to leave the battery and it's going to flow through one light bulb and then directly through another light bulb, and then it'll go back to the battery. So that's called series, when it has to go from the first light bulb to the second light bulb. And then this one over here is going to be called a parallel circuit because the electricity will come from the battery and flow down this first wire, and then it splits up. It splits up and it follows 2 different kind of quote-unquote parallel paths. Some of the electricity will go through this bulb, and some of the electricity will go through this bulb. It's not technically parallel, is it? But I digress. So let's hook them up and see what happens. So there is just our simple circuit, and it has 0.9 amps. And just FYI, right now all of these batteries are set to the same volts, 9 volts, and all of the light bulbs here are identical with the same resistance. So with that circuit, we get 0.9 amps. And remember that this battery you can imagine as like a type of pump, and it's going to pump with a certain amount of kind of force, trying to push the electricity through the wires. So does this one look easier or harder to push the electricity through when I hook it up? It's got to go through one bulb and then through another bulb. To me, it looks like it's going to be harder to kind of push the electricity all the way through that circuit. So I'm probably going to get less current. Half as much current. I had to go through twice as many light bulbs. So that basically doubled the resistance. I had to push through the resistance of one light bulb and then push through the resistance of another light bulb. So that halved our current. This one over here, the parallel circuit, I think is the trickiest. Let me start it maybe by actually disconnecting this. So let's just have this part hooked up. So doesn't that just look very similar to what we had at first? It goes through from a battery, through a light bulb, and then back. And the battery is pushing current through there at a rate of 0.9 amps. So when I hook this other one up and let it kind of create almost a second loop through the battery, so the battery has to power 2 loops worth now. The battery has the same amount of push, but now there's 2 different ways that the electricity can get to the other side of the battery. So the battery is actually pushing the current through twice as fast. So I like to look at the brightness of the bulbs. The brightness of the bulbs will be related to how fast the current is going through there, and the current would heat up the filament and make it glow. So this standard light bulb, let's call this the standard, our base circuit to compare to. That light bulb has 0.9 amps going through it, and it'll be a certain brightness. But so does this one down here. It's the same brightness. And this one, same brightness. So these 3 bulbs all have the same brightness. What I could maybe say is that the main difference between the 2 of them, besides having 2 light bulbs here, so overall you get more light, this battery will get used up twice as fast. It'll run out of its chemicals to create that voltage pump. Right. Now this one is moving current much more slowly through 2 light bulbs. So each of those light bulbs will be dimmer. And as an overall, this current through this battery is the slowest. So that battery will actually last the longest. Another thing that we could do is to look at what would happen if maybe I were to break this connection right here. And the whole circuit shuts down. So you can imagine like the filament in one light bulb breaks, but both light bulbs have to turn off. It just breaks that whole circuit. There's no way now for a loop to be made from the top of the battery to the bottom of the battery. And so if these were Christmas lights with 100 light bulbs, if one light bulb burns out, the whole string is off. Now what about this one? If one of these light bulbs burn out, and so I cut this connection right here, kind of pretending that that light bulb burns out, the other light bulb works just fine. So if these were Christmas lights and you had 100 bulbs all wired in parallel, one light bulb could go out, but the rest would keep working. All right, the last little bit here of section 3 talks about like circuit breakers and fuses and whatnot. So let me just kind of introduce them real quick. Now, circuit breakers and fuses are kind of part of your house's electrical system. And what they do is if there's too much current, they shut off, right? But they are set to shut off, or in the case of a fuse, to burn out. If the wires in your house would probably get hot enough to start a fire in your walls. They will not protect a person from getting shocked or even killed from an electric shock, but they would prevent the wires in your walls from catching fire. Now, the circuit breakers are the newer ones where you can just flip a switch to turn it back on. But when I was a kid growing up, we had fuses. You had to go down and take out the old fuse and put in a new fuse. Okay. But if you want to protect people from getting shocked, GFIs are the way to go. Now, sometimes they're called GFCIs, but they stop the electricity very quickly. Right. And if it senses a small inconsistency of where the electricity might be going, like if the current's coming out of the wall but not going back in to complete the circuit in the right way, it shuts off. And the GFIs will shut off possibly before you even feel a shock. So it does keep you safe. And in the US, it is code to have them in bathrooms and kitchens because that's where your hands are usually wet. But ideally, we should have them throughout the whole house, or even just kind of built in to the circuit breakers down in the basement. And I think they're doing that nowadays, kind of building these in to the circuits. If it does sense that the electricity isn't coming back and it might be escaping through a human, it shuts off right away. Here's an interesting YouTube video, again by the channel Technology Connections. Here's the title of the video if you wanted to search for it. And it just kind of describes what they are and how they work. And one nice thing to know is you don't need them in every single outlet. What you would do though is you need them on the first outlet if your outlets are wired in a stream. So like the electricity might come to one outlet, but then the electric wires can go from one outlet to another outlet, to another outlet, to another outlet. So your outlets might be wired in series, where they follow in a chain. And as long as that first one in the chain is protected by a GFI, so are the others. So I highly recommend that video, and whenever you're putting in new outlets, make sure that it's protected by a GFI. It's just the best way to go, especially when you have kids who get curious. Another thing that this section covers is this third pin. Right? You don't need the third pin for a circuit to work. You really only need these two. So in the case of these outlets, this one hooks up to the hot wire, and that's the wire that is doing the pushing and the pulling of the electricity for the AC electricity. So the electricity here is push, pull, push, pull, push, pull. This is the one that can give you a shock. Right. And then the electricity would go down the wire and do whatever it's supposed to be doing in the circuit, and then coming back, and this is what we call the neutral wire, but really it just kind of goes to ground. It just returns the electricity back to the circuit because electricity needs to have a full loop. So I usually imagine this is kind of the in, and then it goes and does something like lights up a light bulb, and then comes and goes back to the wall to complete the circuit. So what is this for? This is kind of a safety, and it's only useful on certain devices. All right, so we have a quick little video here that'll explain how the hot wire and the neutral wire, those are really the only two that you need to power your device. But this third wire is for safety.
In a typical American outlet, the circuit is comprised of a right vertical slot connected to the hot wire and a larger left vertical slot connected to the neutral wire. The plugged-in device itself, the load, completes the circuit with power flowing through it. So what's the third prong needed for then? This third prong is the ground. Both the neutral and the ground are connected to an earth ground in the main breaker box in your home. The difference between the two is that the neutral completes a circuit with the hot wire and normally carries some amount of current, which is why it's insulated, while the ground does not normally carry any current whatsoever and is not connected to the circuit at all unless something has gone wrong. It simply is used to connect the external conductive parts of the device to the earth and thus, in normal operation, is completely unnecessary. This is why you can use a 3-prong to 2-prong plug adapter to bypass having to use the ground line, and the device will still work just fine. So I have both a neutral and a ground when they both ultimately just tie to the earth ground bar in the main breaker box. Among a few other benefits, this is primarily so that if something should go awry with the device, like a stray hot or neutral wire coming into contact with the outer conductive parts of the device, for instance if the insulation wears away or a wire comes loose, you don't die or seriously get injured if you touch the device and it's plugged in. You see, absent a separate ground in such a malfunction, once you touch the conductive bits of the device, you may become the path to the ground and a surge of electricity would flow through you until ultimately tripping the breaker in your breaker box. With a separate ground, the electricity simply surges through that wire until the breaker is tripped, cutting off power to that line when the surge is detected. This not only helps to ensure you don't get shocked, but also reduces the chances of a fire starting due to the short via making sure the breaker is tripped immediately after the short happens. So what about the devices that lack the third ground prong? How is that safe? They usually have at least 2 layers of insulation between the conductive components of the device and any part of the device you can touch. To achieve this cheaply, the outer casing of these devices are often made entirely of plastic or some other non-conductive material.
So just to add in, like this red hot wire and this neutral wire, that is just part of the normal circuit that might power the radio and whatnot. But what if this red wire somehow got broken or loose and touched maybe this antenna? That antenna would all of a sudden be at 120 volts, and if you touch it, you could get a bad or lethal shock. In case that happened, that antenna and anything metal out here on this case is connected to this ground. Right? So then any electricity that was escaping off of this red wire to maybe that metal antenna, it won't go through you. It'll choose to go through the easier way to the ground to escape, and it'll go through this third prong wire.